So let's continue our conversation about real zeros of polynomial functions. So let's first start with a warm-up where we have a polynomial. We want to state its degree and find its zeros. So what is the degree of this polynomial in part A? The degree is the highest exponent. So we see 2. The key thing whenever you're finding that degree is that it must be in standard form. So now, what are the real zeros? Let's go ahead and factor. F of x is x minus 6 times x plus 1. So each factor is related to a 0. So x minus 6, that means that we're going to have x equals 6 is a 0. X plus 1 would be x equals negative 1. So we have x equals 6, negative 1. And those are the zeros. Now let's look at part B. The degree, again, is 2. Let's go ahead and factor. We have x, and this is a trinomial square, so it factors in x minus 3 times x minus 3. So x minus 3 quantity squared. This means that we have x equals 3, but we obtained it twice, remember? So this would be x equals 3 multiplicity 2. So the degree is 2, and we had 2 zeros. The degree is 2, we had 1 0, but if we count the multiplicity, we had 2. They just weren't distinct. So whenever finding real zeros of a function that's a polynomial of degree n, then we know that our search is limited to no more than n real zeros. So if we have a polynomial that's of degree 7, we will never have more than 7 real zeros. So here we have a graph of a polynomial function. Can this polynomial have degree 3? Why or why not? Well, we know that real zeros correspond to x-intercepts. So we have how many x-intercepts? We have 5 x-intercepts. And so that means that we have 5 real zeros. But we know that if the degree is 3, then that means that we have a maximum of 3 real zeros. So the answer is no. A third degree polynomial would have no more than 3 real zeros. Now, here's a warm-up. We know that negative 1 is a real zero. Can we find the rest of the real zeros of this? Well, we know that if x equals negative 1 is a real zero, then what's a factor? So if x equals negative 1 is a real zero, then x plus 1 is a factor. So let's use that information. Let's divide. So synthetic division would yield for us, now keep in mind that we have a missing term here. So we could rewrite this as x cubed plus 0x squared minus 3x minus 2. So we have 1, 0, negative 3, negative 2. So bring down the 1. multiply, add, multiply, add, multiply, add. And look, we have a 0 for remainder. That means that we did indeed have a factor of x plus 1. So now we can take our function, f of x, and rewrite it as the divisor times the quotient, and then we could put plus remainder of 0, but that plus 0 would go away. So now we have x plus 1, and then we can factor x squared minus x minus 2 as x minus 2, x plus 1. So notice the rest of the real zeros are x equals 2, and we already have stated x equals negative 1 is a real 0. So our remaining 0 is only x equals 2. If we were to list all of the zeros, we could say x equals negative 1 multiplicity two, and then we also have 2. So now we were able to use the fact that negative 1 is a 0 to find the rest of the zeros. What happens if this is not given to us? It turns out that if we have a polynomial function where the coefficients are integers, that means positive or negative whole numbers, then any zeros that are fractions would be found in this set. So we would look at the factors of a sub 0, our constant term, and our factors of our leading coefficient, and we would form any possible fractions from those lists of factors. So factors of our constant over factors of our leading coefficient. So here we go. Let's find the potential rational zeros of the function. So what is our leading coefficient? Our leading coefficient is a sub n, so in this case a sub 5, and our leading coefficient is 2. So we're just looking at this number. So a sub 5 is 2. What is our constant? Our constant is a sub 0, and that is negative 6. The factors of our leading coefficient we'll call q. So what are the possible q values? Q are any factors of 2. So plus or minus 1, plus or minus 2. That's right, we're including any negative values also. And then p will be any factors of negative 6. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And so our potential rational zeros are any p's over q's. So we'll take all of these and divide by all of these. So plus or minus 1, divide by plus or minus 1. Will be plus or minus 1. Plus or minus 2, divide by plus or minus 1. Plus or minus 3, divide by plus or minus 1. Plus or minus 6, divide by plus or minus 1. So we've now taken all of the p's and divided by this q. Now we'll take all of these and divide by 2. So we'll have plus or minus 1, divide by plus or minus 2. That will be plus or minus 1/2. Then we have plus or minus 2, divide by plus or minus 2. But plus or minus 2 divided by plus or minus 2 is plus or minus 1. We've already included it. No need to include it again. Plus or minus 3 divided by plus or minus 2. And then plus or minus 6 divided by plus or minus 2, that's plus or minus 3. We've already included it. So if there are any rational zeros, any fractional zeros, they would be found in this list. How many are in this list? how many candidates do we have? How many possible rational zeros are there? So there are 2, 4, 6, 8, 10, 12, because each one of these has a positive or negative version. So we have 12 candidates in this list. Some of them may be zeros. None of them may be zeros. But if there are any zeros that are rational, they have to be found in this list. So in the last example, we just found the potential rational zeros. We did not actually determine which of those is indeed a zero, if any of them were. In this example, however, we will take that step of not only finding the potential rational zeros, but we will actually determine if any of those are zeros of the function. So, in this example, our leading coefficient is a sub 3, because it's a third degree polynomial, and it's equal to 6. Our constant term, a sub 0, is negative 2. So, Q will be any factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. P will be any factor of negative 2, so plus or minus 1, plus or minus 2. So, the P's over Q's are the potential rational zeros. So, we will take 1 and 2 and divide by 1. Then we'll take these and divide by 2, then divide by 3, and then divide by 6. So, plus or minus 1 divided by 1 is plus or minus 1. Plus or minus 2 divided by plus or minus 1. And now we'll move to dividing by 2. So we'll take 1 divided by 2 and 2 divided by 2. So plus or minus 1 divided by 2 is plus or minus 1/2. Plus or minus 2 divided by plus or minus 2 is plus or minus 1, which we've already included. Now we'll move to dividing by 3. So plus or minus 1 divided by plus or minus 3 is plus or minus 1/3. Plus or minus 2 divided by plus or minus 3 is plus or minus 2/3. Now we'll divide by 6. So plus or minus 1 divided by 6 is plus or minus 1/6. And then plus or minus 2 divided by plus or minus 6 is plus or minus 1/3, which we've already included. So how many candidates for potential rational zeros do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 potential rational zeros. 12 candidates. So let's start. And what I do is I typically start with 1, then I go to negative 1, then 2, then negative 2, and I make my way down the list. I start with the whole numbers typically, or the integers, before I get to the fractions. So let's start with 1. How do we check to see if it's a 0? Probably the easiest way is to check with synthetic division, and if you end up with a remainder of 0, you can use that to help factor your polynomial and move on. So let's start with 1. So we're going to try 1, and we have 6, 11, negative 7, negative 2. Always make sure that you don't have any missing terms in that dividend. So where do these come from? These are just the coefficients of our function. So let's bring down the 6. Multiply 1 times 6 is 6. 17. Multiply. Add. Multiply. Add. So we get a remainder of 8. So 1 is not a 0. So let's try negative 1. So bring down the 6, multiply, add, multiply, add. Now multiply negative 1 times negative 12, and that gives us positive 12, and that yields for us positive 10. So again, not a remainder of 0, so negative 1 is not a 0. Let's move on to our next in our list. So move back to our list. We had positive or negative 1. We've checked both of those. Let's move to positive 2. So 6, 11, negative 7, negative 2. Bring down the 6. 2 times 6 is 12. Add. 2 times 23 is 46. Add, and we get 39, 78 when we multiply, and that gives us 76. So let's try negative 2. Bring down the 6. Negative 2 times 6 is negative 12. Add, and we get negative 1. Negative 2 times negative 1 is positive 2. Negative 7 and add 2 is going to give us negative 5. Negative 2 times negative 5 is positive 10. That gives us 8. So let's now look at the next in the lineup. So let's look at 1/2. So bring down the 6. 1/2 times 6 is 3. Add. 1/2 times 14 is 7. We get 0. 1/2 times 0 is 0. And we get a remainder of negative 2. So 1/2 is not a 0. So let's try negative 1/2. Bring down the 6, multiply, add those, and we get 8. That gives us negative 4, and then negative 7 plus negative 4 is negative 11. This gives us positive 11 halves, and that would yield for us negative 2 plus 11 halves, 7 halves. Again, not 0, so it's not a 0. Negative 1/2 is not a 0. So let's move on. That's 1/2 and negative 1/2. Let's look at 1/3. Bring down the 6. 1/3 times 6 is 2. Add. 11 plus 2 is 13. Multiply. That's 13 thirds. Add, and we get negative 8 thirds. Multiply, and we get negative 8 ninths. And then add, and we get negative 26 ninths, which is not 0. So again, this is not a 0. So let's try negative 1/3. So you can already tell that this is an arduous task. Keep in mind that we might get through this whole list and none of them are zeros. We're not guaranteed rational zeros. So bring down the 6. Negative 1/3 times 6 is negative 2. Add, we get positive 9. Multiply, we get negative 3. Now we have negative 10. So this is going to be positive 10 thirds. And I could stop because this is not 0. Negative 2 plus 10 thirds is 4 thirds. So it's not negative 1/3. So let's try, the next in the lineup would be positive 2 thirds. So bring down the 6. 2/3 times 6 is 4. 11 plus 4 is 15. 2/3 of 15 is 10. Negative 7 plus 10 is 3. 2/3 times 3 is 2. Add those. We get 0. So let's take inventory of what this means. X equals 2/3 is a 0. This also means that x minus 2/3 is a factor. So at this point, we have p of x equals our dividend, x minus 2/3, times our quotient, 6x squared plus 15x plus 3. Now, we know x minus 2/3 is a 0. Sorry, x minus 2/3 is a factor, so that gave us that 0. We now need to find the remaining zeros. So we can look at our depressed polynomial, 6x squared plus 15x plus 3. So let's look at 6x squared plus 15x plus 3 equals 0. This is quadratic, so we can go ahead and either factor this or use quadratic formula. Well, it does not factor. I can divide everything by 3, and that'll at least make the number smaller. So we have 6x squared will become 2x squared plus 5x plus 1 equals 0. And so x equals negative 5 plus or minus the square root of 5 squared minus 4 times 2 times 1. This is all over 2 times 2. So this equals negative 5 plus or minus the square root of 25 minus 8 all over 4. So our solutions, our zeros, are x equals 2/3, and then negative 5 plus or minus the square root of 17 all over 4. So you'll notice there's 1 0, and then we have negative 5 plus the square root of 17 over 4, and then negative 5 minus the square root of 17 all over 4. So we have 3 real zeros for our third degree polynomial. So that is our final answer after much work. So here we are going to factor our polynomial, which we've already started to do. P of x equals x minus 2/3 times, we had 6x squared plus 15x plus 3. Now, we noticed that there was a 3 in each one of those terms, so let's factor out that 3 in front. So 3 times x minus 2/3, and then we had x squared plus 5x plus 1. So we have 3 times x minus 2/3. And then x squared plus 5x plus 1 did not factor beyond this as linear factors like we traditionally do, but we do know that if x equals c is a 0, then x minus c is a factor. So we had x equals negative 5 plus the square root of 17 over 4. So we would have x minus negative 5 plus the square root of 17 over 4. But not only did we have negative 5 plus the square root of 17 all over 4, we had negative 5 minus the square root of 17 over 4. So x minus negative 5 minus the square root of 17 over 4. And so there is our factored polynomial. This time we factored over the reals, not just rationals like you had done in an Algebra 1 or Algebra 2 course. Okay, so let's look at another example. Hopefully this won't be as arduous. So if we look at our leading coefficient, it will be a sub 5, and that is 2. Our constant is a sub 0, and that's 72. So our q's will be positive or negative 1, positive or negative 2. Our p's will be all the factors of 72, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 24, plus or minus 36, plus or minus 72. So those are all of the factors of 72. So now we take each one of those, divide by 1, which will just be that same list, then all of those divide by 2. So our potential rational zeros, our p's over q's, will be the set plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 24, plus or minus 36, plus or minus 72. And then we keep going. That's all of the p's divided by 1. Now we take all the p's divided by 2, and we don't repeat any that we've already listed. So we have plus or minus 1/2. But now we have plus or minus 2 divided by 2, and that's plus or minus 1, which we've already listed. So plus or minus 3 divided by 2, plus or minus 4 divided by 2 we've already listed as plus or minus 2. Plus or minus 6 divided by 2 we've already listed as plus or minus 3. Plus or minus 8 divided by 2 we've already listed as plus or minus 4. Plus or minus 9 divided by 2, we have plus or minus 9/2, so that's a new one. And then we have plus or minus 12 divided by 2, we've already included. And then 18 divided by 2 is 9. 24 divided by 2 we've already included. 36 divided by 2, and 72 divided by 2 we've already included. So that rounds out our list. So we just need to check those into our original function. I would double check to make sure there are no missing terms. So 5, 4, 3, 2, 1, 0. We're good. So let's start off with trying 1 out. So we'll take our coefficients of our polynomial, 2, negative 13, 19, 34, negative 108, 72. Bring down the 2. 1 times 2 is 2. Add, multiply, add, multiply, add, multiply, and then add, and then multiply, and then add. So we don't get 0. So 1 is not a 0. Let's try negative 1. Hopefully this isn't like the last problem when we get through a bunch of them before we find something. So bring it down, multiply, multiply, so we have 180, which is definitely not 0. So let's try our next one. Let's try 2. So let's bring down the 2. Multiply. Now if we add, we get negative 9. That's going to be negative 18. Add those and we get positive 1. That's going to give us 36. 72. This gives us negative 36, which yields for us negative 72, and that gives us a remainder of 0. So x equals 2 is a 0. And so x minus 2 is a factor. Now, what can we say? We've just found a factor of g of x. So g of x is now equal to x minus 2, since it's a factor, times, and then we can use our quotient. So we have 2x to the 4th now, minus 9x cubed, plus 1x squared, plus 36x minus 36. Now, what we can do is we can really focus on finding the remaining zeros of this. So, now, 2 was a 0 once. It could have multiplicity, so we should check 2 again, but it wouldn't make sense to check it in this again, we already know. So if 2 is a 0, it would be a 0 of this again. So let's try that. So bring down the 2, multiply, add, multiply, add. We get negative 18. That's going to be positive 18. This is going to be 36, which yields 0. So indeed, it was a 0 again. So what's this mean up to this point? It means that this portion could factor as x minus 2 times 2x to the 3rd minus 5x squared minus 9x plus 18. But let's put this all together. This means g of x equals, we've said x minus 2 is a factor twice now. And if we factor out the x minus 2, we get 2x cubed minus 5x squared minus 9x plus 18. Now our attention can focus on this cubic. So x minus 2 was a factor once, it was a factor twice. What if it's a factor again? So let's check again. Let's do our synthetic division, but again, we're going to focus on this depressed polynomial. 2, negative 5, negative 9, positive 18. So notice we're making some progress. We're getting to a smaller and smaller polynomial. So let's bring down the 2. 2 times 2 is 4. We get negative 1. 2 times negative 1 is negative 2. This is negative 11. This yields for us negative 22, which is a negative 4, which is not 0. So we're done with 2. Let's move on down the list. Our next is negative 2 in the list. Now where will we try negative 2? Do I go back to the original polynomial? No, I don't have to do that. We could, but it would make sense to just keep working with what we got. So 2x cubed minus 5x squared minus 9x plus 18 could potentially have negative 2 as a 0. Let's try it. So 2, negative 5, negative 9, positive 18. Bring down the 2. Multiply. Now, negative 2 times negative 9 is positive 18. Add, we get 9. Multiply, we get negative 18, which is 0. So, x equals negative 2 is a 0. That means x plus 2 is a factor. So now we've said g of x equals x minus 2 quantity squared times x plus 2. And now what are we left with? We can go back and look at this, and that is the remaining portion. So 2x squared minus 9x plus 9. Now let's continue. Let's focus on the 2x squared minus 9x plus 9. So 2x squared minus 9x plus 9, that's quadratic. We can solve that. We can either use quadratic formula, which would always work, or we can try to factor. So let's try factoring. So we have x and 2x, and the signs would have to be the same, and they both have to be negative. Let's try minus 3 and minus 3. That gives us negative 6x and negative 3x. That yields our negative 9x. So we know our factors work. So we have x equals 3 and x equals 2/3. Sorry, x equals 3 halves. So what do we have? Our zeros we have found to be 2 multiplicity 2 negative 2, 3, and 3 halves. So notice how many we have found. 1, 2, 3, 4 real zeros. If we count multiplicity, we get 5. But notice the degree of our polynomial was 5, so we should find 5 or less real zeros, which we have done. So let's factor this. We know that our zeros were 2 multiplicity 2, negative 2, 3, and 3 halves. Each one of those will correspond to a factor. So x minus 2, the multiplicity will yield an exponent. X plus 2, x minus 3, and x minus 3 halves. So g of x will be those factors multiplied together. But now if you multiply this out, what do you get? You get something x to the 5th. You get x squared times x times x times x. That's x to the 5th. We need 2x to the 5th. So we'll multiply by a 2. And there is your factorization. So solving this equation is much like what we've been doing. The first thing that we need to do, though, is we want integer coefficients. Right now we have some fractions in the mix. So let's multiply everything by 2 and clear the fractions. So I can do that because this is an equation. So I'll multiply the left side by 2 and the right side by 2. And that would yield for us 2x to the 5th minus 17x to the 4th plus 50x cubed minus 62x squared plus 32x minus 5 equals 0. Now why did I do that? If you go back and you look at the rational zeros theorem, it requires the coefficients to be integers, so no fractions. So now we'll check our a sub 5 is 2, that's our leading coefficient. This means that our q's are plus or minus 1, plus or minus 2. And now a sub 0 is our constant term. It's negative 5. That means that the p's are plus or minus 1, plus or minus 5. So our potential rational zeros, our p's over q's, are going to be take the 1 and the 5, divide by 1, and then take the 1 and the 5 and divide by 2. So we get plus or minus 1, plus or minus 5, plus or minus 1 half, plus or minus 5 halves. So we have 8 candidates here. So let's check these by synthetic division. Let's start with 1. So I will be checking them with this polynomial on the left-hand side of this equation. So we have 2, negative 17, 50, negative 62, 32, negative 5. Let's bring down the 2. 1 times 2 is 2. Negative 15 when we add. Multiply. Add. Multiply. Add. Multiply. Add. Multiply. We get 0 for a remainder. That means x equals 1 is a 0. But that's a 0 of the polynomial. That means it's a solution to the equation. So now what this means is that we can go ahead and focus on 2, negative 15, 35, negative 27, and 5. So if it is a solution once, it might be a solution twice. That 0 might have multiplicity. So let's check 1 again. So we'll have 2, negative 15, 35, negative 27, and 5. So bring down the 2. 1 times 2 is 2, negative 13, multiply. Now 35 minus 13 is 22, multiply, add, multiply. It's a 0 again. So now we can focus on 2, negative 13, 22, negative 5. Let's check 1 yet again. It might have multiplicity of 3. So 2, negative 13, 22, negative 5. Bring down the 2. 1 times 2 is 2. That's going to be negative 11. Multiply, add, and the luck has run out, is not a 0 again. So let's move on and let's go down the list. Let's look at x equals negative 1. So we have I'm going back to the last depressed polynomial, the 2, negative 13, 22, negative 5. So bring down the 2. Multiply. Add. Multiply. Gives us positive 15. Now adding, we get 37, and that's not going to work. That's negative 42. So no dice there. Let's go down the list. Let's check 5. Let's put 5 in. So 2, negative 13, 22, negative 5. Bring down the 2. 5 times 2 is 10. Add, multiply, add. 5 times 7 is 35. That gives us 30 when we add. So let's try now negative 5. Bring down the 2. We have negative 10. That's negative 23. That's going to be, my negative disappeared. So negative 5 times negative 23 will be a positive 115. If I add those, the 22 and the 115, that gives us 137. Multiply, that gives us negative 685, which is going to yield negative 690. Definitely not working there. So let's go down our list. Let's look at positive 1/2. So bring down the 2. 1/2 times 2 is 1. That's going to give us negative 12 when we add. 1/2 times negative 12 is negative 6. 22 minus 6 is going to be positive 16. 1/2 times 16 is 8. That gives us positive 3. So that's not working. Let's try negative 1/2. 2, negative 13, 22, negative 5. This is an exercise in patience. Hopefully you're staying with me. Bring down the 2. Negative 1/2 times 2 is negative 1. That gives us negative 14. Negative 1/2 times negative 14 is positive 7. This gives us 29. That's negative 29 halves. And that gives us 39 halves, which is negative. That's not 0. So let's move down the list. Let's look at positive 5 halves. 2, negative 13, 22, negative 5. Bring down the 2. 5 halves times 2 is 5. This gives us negative 8. That's going to give us negative 20, which gives us positive 2, which gives us positive 5, which yields 0. So indeed, we get 5 halves is a solution because 5 halves is a 0. So what have we said up to this point? We have said that our solutions are x equals negative 1 multiplicity 2, and we've seen 5 halves. Well, now we're down to a quadratic. So let me take 2x squared minus 8x plus 2, and let's set that equal to 0. We don't have to keep doing synthetic division because now we're down to a quadratic. Once you hit a quadratic, 3 terms in your quotient, you stop. Now we can go ahead and use a quadratic formula, or we can try factoring. Regardless, at this point, everything is divisible by 2. So this gives us x squared minus 4x plus 1 equals 0. That does not factor, so let's use quadratic formula. Negative, negative 4 plus or minus the square root of the square of negative 4 minus 4 times a times c all over 2a. So that gives us 4 plus or minus the square root of 12 over 2. That's 4 plus or minus 2 square roots of 3 over 2. Out of the numerator, we can factor out a 2. And cancel. And so we have 2 plus or minus the square root of 3. So let's take inventory and state all of our zeros now. So we have x equals negative 1, multiplicity 2, 5 halves, and now we have 2 plus or minus the square root of 3. Notice there are 2 solutions there. We have 2 plus the square root of 3 and 2 minus the square root of 3. So we have 1, 2, 3, 4 solutions. If we count multiplicity, then there's our 5th.